Hello and welcome. Today we're going to be looking at geometric series. So previously we've done some work with arithmetic series and arithmetic and geometric sequences. So again, a reminder what a series is. A series is the indicated sum of the terms of a sequence. And we really consider two types of series: a finite series, which has a first term and a last term, so a beginning and an end. And we also consider an infinite series, which continues without end. So we'll take a look at those things for geometric series. Next, we'll take a look at kind of a brain teaser puzzle type problem. And so once we go through these notes, maybe you can come back to here and give this one a thought. So it's kind of an old tale. Involves a soldier who rescues his king in battle. The king grants him any prize within reason from the riches of the kingdom. The soldier asks for a chessboard with a single kernel of wheat on the first square, 2 kernels of wheat on the second square, then 4, then 8, and so on for all 64 squares of the chessboard. The king decides that the request is reasonable. So that's how the story goes, and I've heard the similar story, just different details depending on the culture. So after having worked with some geometric series, you'll be able to come back to here and try to figure this question out. The other part of this question concerns U.S. wheat production. So a bushel of wheat contains about 1 million kernels. The total U.S. output of wheat in a recent year was just over 2.1 billion bushels. And so the question would be, how many years of production at that level would it take the United States to produce enough wheat to satisfy the soldier's reasonable request? So kind of a two-part brain teaser here for you to get into, again, after you've learned a little bit about geometric series, and see if we can come back and maybe you can figure this question out. So just like with a finite arithmetic series, we can find the sum of a finite geometric series using this formula. You do need to know the first term, the number of terms, and the common ratio. So again, those are the three pieces you need: the first term, the number of terms, and the common ratio. And again, just a reminder that a geometric series is the sum of the terms of a geometric sequence. So our sum formula here says the sum of those terms equals our first term, a sub 1, multiplied by the quantity 1 minus r to the n power, where r is the common ratio, n is the number of terms, and all over 1 minus r. So not a lot of variety there to the different pieces. We've got the first term, 1 minus r to the n, and then just a plain 1 minus r. So that's our sum for a finite geometric series. Just to compare, that formula for the sum of a finite arithmetic series looks like this, where you take half the number of terms, that's the n over 2, multiplied by the sum of the first and last terms. So you're going to want to become familiar with both of those, understand the differences, and know when to apply which one. Of course, here we're looking at finite geometric series, and so they give us our series here, 3, 6, 12, 24, 3072. Well, in order to use our formula for a finite geometric series, we need the first term, we need the ratio, we need the number of terms, and then that's really it. We need that ratio again. So we will have to, well, getting the first term easy enough. The first term is 3. Getting the ratio isn't so bad. Again, we're told it's geometric, so we really just have to compare the second term to the first term. 6 divided by 3 gives us 2, so that's our ratio. Finding the number of terms will be similar to what we had to do with our finite arithmetic series. What we like to do is write our explicit formula for the geometric sequence that would go along with this series. So that formula would look like this: a sub n would equal the first term 3 times the ratio 2 to the n minus 1 power. And then we go ahead and replace a sub n with our last term, in this case 3072, and we try to figure what the value of n is for 3072. So we'd start by dividing both sides by 3. and we get 1024, so that would equal 2 to the n minus 1 power. So again, what we did there is divided both sides by 3. Now we have an exponential equation. Well, I imagine that. So we're wondering 2 to what power is 1024. Now in this case, one thing we do have on our side is we know that n has to be a whole number. It can't be a decimal or fraction. So we do have that on our side. So we know 1024 must be a power of 2. So if you think back to our exponential unit, we could solve this using the common base method, because 1024 is a power of 2. Specifically, 1024 is 2 to the 10th power. So again, that's how we're going from here to here. We're saying that 1024 is 2 to the 10th power. So 2 to the 10th equals 2 to the n minus 1. So then, if that is true for this case, then 10 has to equal n minus 1. And so n would equal 11. Sometimes people get a little confused there and want to say then that n is 9. Of course, that would be backwards. N is 11. So we have the three pieces we need for our formula. And again, get accustomed to the formula and how it's put together. So we take our first term, so the sum of these 11 terms will equal the first term, which is 3, times the ratio 1, or times the quantity 1 minus that common ratio, which is 2, to the n power, which is 11, over 1 minus 2. We can let the calculator do most of the work there. As far as figuring out what we have, I would recommend doing kind of little pieces here so as not to make mistakes. The numerator turns out to be negative 6,141, but the denominator is a negative 1, so we end up with 6,141 for the sum of that finite geometric series. Alright, so we looked at a little bit of this summation notation previously. Again, the way that this works is we can use the Greek capital letter sigma to indicate a sum. We use limits to indicate how many terms you are adding. So limits are the least and greatest values of n in the series. You write the limits below and above the sigma to indicate the first and last terms of the series. So you can translate a series like the one that we have here to summation notation, so like a 3 squared plus 4 squared plus 5 squared all the way up to 108 squared. One way to write this, and again there can be multiple ways to do this. You can write it as first term is when n is 3, last term is when n is 108, so then it would just be n squared to describe that series. So really the first term is when n is 3, so again it can be a little bit different there for figuring that out. If you do have an infinite series, there will be an infinity as the upper limit. You could start wherever, it would still be infinite. In order to find the number of terms in a series, you take and subtract the lower limit from the upper limit. So in this case, 108 minus 3, and then add 1 to get 106. Again, an example would be if you have terms from 1 to 10. We all know there's really 10 terms there. 10 minus 1 would be 9. You add 1 back in to get back to 10. So that's a little bit on summation notation. So here we want to find the sum for a finite geometric series that's written in summation notation. Some key points here. Notice the first term happens when n is 0 in this case. So we do need, remember the things that we need for our summation formula for a finite geometric series. We need the first term, we need the ratio, the number of terms. So those three things, that is what we need. So to figure out the first term, we plug a 0 in for n. Okay, the first term happens when n is 0, so a sub 1, which is the first term, but again that happens when n is 0, but a sub 1 would be 4. 1/2 to the 0 power would be 1. 4 times 1, of course, is 4. So we've got the first term. We also need the ratio. In this case, the ratio comes right from the expression describing the rule. So we're repeatedly multiplying by 1/2, and so that would be the ratio. An alternative way to find that ratio is we found the first term. We'd go ahead and find the second term, which would happen when n is 1. When n is 1, we'd have 4 times 1/2, which would be 2. And then you could even continue in finding terms there and realizing that it is geometric. Of course, they told us that as well. And then you could find the ratio would be 1/2. So again, you don't necessarily have to just pull it off of the rule. You could also create figure out a few terms in that sequence to figure out the ratio. So the last thing we need is the number of terms. And again, here it goes from 0 to 20. So we do 20 minus 0 plus 1 in order to get the number of terms. And so we end up with 21 terms. So now we've got all the information we need to plug into our formula. And again, the more times you write this formula down, the easier it's going to be to remember. So the sum of those 21 terms is the first term, 4, times 1 minus the ratio, which is 1/2. Now, I'll put parentheses on that. Since there is a 1 in the numerator of that 1/2, I don't necessarily need them there. But really the 2 needs to be taken to the 21st power, so that's the important thing. And then just, not sure why I put those on the 1/2 in the denominator, but I did, and it's not a problem, so there we go. Again, be careful on your calculator the way that you figure this. I would recommend, again, maybe figuring out the numerator first, and then divide it by the denominator. In this case, the numerator becomes approximately, so I'm just going to kind of write out a little bit of this, 3.99999, and I keep the rest of that in my calculator, but just not going to write out all of it. And you're dividing that by 1/2, so really the same as multiplying that by 2, and if we really kind of approximate this, although not too much, it's 7.99999, so really turns out to be about 8 for that sum. So sum for those 21 terms gets infinitely close to 8, so we can round it there. So here are a couple problems for you to try. So again, you can go ahead and pause, then I will go through these in just a minute so you can check to see if you got the same thing that I did. Alright, so looking at this first one, again, we know what we need here. We need our first term. We need 1 minus the ratio to the n power, and we need 1 minus the ratio in the denominator. And again, they do identify that, yes, they are geometric series. If they didn't tell us that, we should be able to look at that and figure that out, because we can see that the common ratio here would be -2. So that's one of the things that we need. We also need the first term. First term would be -15. And then the number of terms here, we can just count them. We've got 6 terms. So really, I mean, in this case where they show us the whole series, I suppose if you really wanted to, you could just add them together. But again, we really need to practice using our formula. So the sum of those 6 terms would equal the first term, -15, times 1 minus that ratio of -2 to the 6th power. And the parentheses are important there because the entire -2 has to be taken to the 6th power. And then 1 minus the -2. So again, be very careful on how you enter this into the calculator. The numerator turns out to be 945. And of course, we'll be dividing that by 3, because 1 minus the -2. And we end up with 315 as our sum. So again, like I said, also with the whole series there in front of us, you could just add those up to verify that that is correct. All right, moving on to our series that we've got described in the summation notation. So again, we need to look at the same pieces. What is the first term, what is the common ratio, and what is the number of terms? First term, notice, so that first term ends up being 5. Again, you can plug the 1 in there, you end up with negative 2 to the 0 power. The ratio would be the negative 2, number of terms is 10, so we again plug in our different values into our formula. So again, we get that first term 5 times 1 minus that ratio negative 2 to the n power. Oops, there we go. And and then over 1 minus r, so 1 minus the negative 2. Again, be careful how you calculate that. The numerator turns out to be negative 5,115. Dividing that by 3 gives us negative 1,705. Alright, so here we're taking a look at an application problem. So you set aside $100. Each month thereafter you plan to set aside 10% more than the previous month. So then in the second month you'd be adding $110. In the third month you would be adding $121, and so on. The question, how much will you save in 10 months? So the first term being 100, the rate really being 110% or 1.1, and that's what we're multiplying by because we're adding 10%, so 1.1, and the number of terms would be 12. So our sum formula would look like this. The sum of these terms would be the first term 100 times 1 minus 1.1 to the 12th power over 1 minus 1.1. Again, just careful on the calculator with these. The final total to the nearest cent ends up being $2,138.43. So we've been working with finite geometric series. The other concept is an infinite geometric series, and again you may want to pause and read through this in detail. I'm just going to kind of highlight and paraphrase. So an infinite geometric series has a first term a sub 1, common ratio. If that common ratio has an absolute value of r that's less than 1, so in other words, if the r value is, say, like a half or 2/3 or even a negative 1/2 or negative 2/3, something like that, but it's got the absolute value of it has to be less than 1, then it will have a sum, and then that sum is just this form here. It's just the first term over 1 minus r. If, however, the absolute value of r is greater than or equal to 1, then the infinite geometric series does not have a finite sum. And that's because those values just continue to change so much that they will not converge on a single value. And that's really what we say that this sum will do. It will converge to a particular value. If the, and again that happens if the absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, then it will diverge, so it will not have a sum. So for these, again, if it converges, then the sum would equal the first term over 1 minus r. And again, the more often you write this formula, the easier it will be to remember. So in our first infinite series, we've got 1 and then 1/2 and 1/4. So the r value is 1/2. So it will fit our pattern here because the absolute value of r is less than 1. We already have r. We just need the first term, which is 1. So the sum for this one would be 1 over 1 minus 1/2. So really 1 over a half, which would just be 2. So that's the sum of that infinite geometric series. So even though it goes on forever, it still just approaches 2 as we get towards that infinite number of sums. Now looking at example B, they do write this in summation notation. We should still, however, be able to pull out the common ratio there. It's negative 5/4. Well, the problem is negative 5/4 is greater than, or the absolute value of it is greater than 1. So this one would diverge. So it will not have a sum. Over here, I guess I never wrote it down, but again, this one converges. So when it converges, then we can figure out the sum using that formula. So here's a couple for you, or three for you to try. So you can go ahead and pause, and I'll go through this in just a second here. Alright, so for this first one, again, we have to figure out if it converges or diverges. So first of all, they don't necessarily tell us that they are geometric, so we want to figure that out. So here the R value is 1.5, so this one would diverge. It is geometric, but the R value, absolute value of R is greater than 1, so it will diverge. For number 2, the R value is really negative 1/3. Again, it's okay that it's negative, so the sum will just be the first term 1/3 over 1 minus 1/3. So really we get 1/3. So 1/3 over 2/3 here. Now, of course, your calculator can handle that, but that would be 1/3 times 3/2, which ends up to be 1/2. And so that's the sum for that infinite geometric series, is just a half. And then if we look at the last example, now they did write this one in summation notation. We can see from here that the R value is 2/3, so it will converge. So since it converges, then we can use our formula to find the sum. So the sum will equal the first term, which if we plug the 1 in, would give us 2/3 over 1 minus that ratio, which is 2/3. So we get 2/3 over 1/3, which of course would be the same as 2/3 times 3, which would just be 2. So that's the sum for that infinite geometric series.